Hello GATE aspirants and welcome back to the fast track revision course for GATE exam, and the running subject is control system. This is lecture number 2 of chapter 2 of control system, and the topics that we will cover in this lecture is marginally stable, meaning we will understand the meaning of marginally stable system, unstable system, and then we will learn the special cases of Routh Hurwitz criteria that we have done in the previous class. That was the basic Routh Hurwitz table, and we have learned the Routh Hurwitz stability criteria. In this lecture we will learn some special cases of Routh Hurwitz criteria. So let's start from the first topic, that is marginally stable and unstable system. So about stable system we have already studied, but we will compare here the three types of system: stable system, marginally stable system, and unstable system. So the definition, the rule is on your screen itself. Stable system: all poles in left half plane, means if a system having all of its if I am talking about a system, then it means it is a control system, and moreover a control system is a causal system, means st equals to 0 for t less than 0. There is no transfer function, means value of transfer function will be 0 for t less than 0. So basically we are talking about the causal system, which is a control system, and so we will define the stable, marginally stable, and unstable in that way. Okay, so stable system: if all the poles of an system lies in the left half as plane, then it will be called stable system. Now come to the marginally stability, means for a stable we have already understood that if this is S plane, this is real part of S, and this is of course imaginary part of S, this axis. And when we are talking about a stable system, then all the poles must lie in this region, means here in this region all the poles should lie either on the real axis, it should lie, or it can be a complex value as well, but all the poles should be in left half S plane. Next, when we come to the marginally stable system, then in that case one pole, means there can be poles on imaginary axis but with multiplicity 1, means no multiplicity basically means if we are talking about the imaginary axis and there is a pole, conjugate pole of course on the imaginary axis, then it is okay, it has multiplicity 1. But when we are talking that there are two poles on the same position, two conjugate poles on the same position, then it has multiplicity 2. So for the case when there is only multiplicity up to 1, then it will be called marginally stable system, and plus all poles should be in left half plane. So overall the marginally stable system will be like this, that all poles lie here in the left half as plane, and one pole on the, or you can say poles, conjugate poles on the imaginary axis with multiplicity 1. Okay, and one more thing, if there is a pole on origin, suppose s equals to 0, then it can also be stable, but it also have the must have the stability means multiplicity 1, that is there should be only one pole at origin. Otherwise if there is two poles at origin, then it will be unstable again. So for checking the marginally stability, we must check that, ensure that on imaginary axis the conjugate poles or the poles having multiplicity 1, and plus all the poles lie in the left half S plane. Now come to the last system, that is unstable system. When we are talking about the unstable system, then it can have two conditions: either any one pole is in right half plane, means whether the all poles lies, it doesn't matter, but if any pole lie in the right half S plane, then that system will be unstable. One more condition for instability is that, suppose if there is no any pole in the right half S plane, means if a condition is like that there is no any pole in the right, there is no any pole in this right half plane, but there is conjugate poles or poles on imaginary axis with multiplicity more than 1, means either multiplicity is 2, 3, anything, means there are multiple poles on imaginary axis at same point, then that will also cause instability. So instability can be in two manner: either any one pole, any single pole in right half plane, or there is means all the poles in left half plane, but there is poles which is on imaginary axis having multiplicity more than 1. So these are the three conditions for stability, marginal stability and instability of a system. Now come to the point how we can find the position of poles, means using the Routh Hurwitz criteria. In previous lecture we have studied how to know the stability, means if all the columns of a Routh Hurwitz table is positive or of same sign, then we call it a stable system. But how can we find, means suppose it is unstable. If it is stable, then all the poles will be in left half plane, but suppose it is unstable, then in that case how we can determine that how many number of left half S plane and how many number of right half S plane? If we have to decide it, then how can we decide? So this can be decided by number of sign changes in the first column. Suppose we have the positive sign, and then suddenly a negative sign comes, then again the positive sign comes, then again a negative sign comes, then positive, and so on. If this type of column is formed, this type of Routh table is formed in which the first column element are in this way, that first element of the first column is positive, next one is positive, again next one is negative, so on, then in that case what we have to count? We have to count the number of sign changes. From here if we will start, then no sign change, yeah, one sign change is here, again one sign change is here, because we are moving from minus to plus. Again when we are moving to plus to minus, again one sign change, again minus to plus, one sign change, and there plus to plus, no sign change. So sign is changing 1 2 3 4 times. So in this way we can calculate the number of times the sign is changing in the first column elements. So as much as the number of sign change will be, the same number of right half plane right half S plane poles will be there. So here I have written the formula for calculating the number of poles in the right half S plane. So number of sign changes in first column will be equal to number of poles in the right half S plane. Now what about the number of poles in the left half S plane? So of course by checking the order of the characteristic equation, we can easily determine what is the total number of poles. Suppose we have the equation like in this form, s power 5, so on so on. So the order of the characteristic equation is 5, then there will be 5 roots of the characteristic equation, that is basically there will be 5 poles. So out of 5 poles, whatever number of the right half S plane poles will be subtracted, and then the remaining will be in left half S plane. So the same formula I have written here, number of poles in left half plane will be equals to total number of poles that will be decided by the order of the characteristic equation minus number of poles in the right half plane. So this way we determine the total number of poles in right half plane and total number of poles in left half plane using the basic Routh table that we have studied in the previous lecture. Let's check some questions related to this topic, this concept. So the question is on your screen. The number of roots of this that lie in the left half of the S plane, the same as I discussed. What we this is characteristic equation, and we have to decide what is the number of left half S plane. So how we can decide? A strategy will be like that. First of all, we will form the Routh table, and then we will check how many times number of sign is changing. The same number of poles will be in right half plane, and then we will decide the number of poles in the left half plane. So check the solution. It is the solution for the question. So we had the equation, the characteristic equation, for which we have formed the first 2 rows 1 7 and 5 3. Now calculating the second means the rest of the table, means completing the Routh table, we get this result. Now by this result, by seeing this result, we see the first column elements, and we can check that there is no any sign change, means here from we are going positive, 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 all are positive. So there is no any sign change. No sign change means no root in the right half plane. So all the poles in the left half S plane, and that means whatever the order, means order is of course 3. So the poles, 3 poles will be in left half of S plane. So this way we can solve this question. Next come to the topic, that is special cases of Routh Hurwitz criteria. So there will be basically 2 special cases, and how it can be. So if we are forming the Routh Hurwitz table, then in that case one case can come like this, that first element, means first column element can become 0. When it happens, suppose here we have got 0, then if we will try to find the next row, then in that case we will have to divide by 0, so it will lead to inexistence. So next row cannot be formed if we take it as 0, so there will be a problem to complete the Routh table. Now for solving this type of case, how we will approach, it is mentioned in this slide. So suppose we have the characteristic equation like this. So we have written the first two row by using the coefficient of the characteristic equation and formed the next row, and in next row suppose we have got this 0. Then for solving further the Routh table, for completing the Routh table, what we will do, we will take 0, means replace 0 by a small positive value epsilon. So once we will replace 0 by epsilon, then it can be, means now it can be put in denominator and the Routh table can be completed. So this way we will complete the Routh table using that small epsilon value, and then after finally to analyze the result, what we will take, means epsilon will limit will be put, epsilon tends to 0, and then further analysis will be done. So in this way we can solve this problem. One more method is there, that if we have to find only the left half, means for characteristic equation, using characteristic equation, what we used to find, only stability, and the second thing that we find is the where is the position, what is the position of the poles, means either it is lying in left half plane or right half plane or imaginary axis. So that is the concern only. So for checking only that thing, what we can do, we can replace s by 1 by z and form a new characteristic equation. Suppose this is the new characteristic equation for this equation, and that was the original characteristic equation, and we have replaced s by 1 upon z and formed the characteristic equation in this manner. Now what will be the benefit of this is that by solving this new characteristic equation, whatever the position of the root of the poles will be analyzed, the same will be the position for the poles for this original characteristic equation. Why? So suppose we have s equals to -2 that lie in left half plane, then of course if we are taking inverse of it, that is z equals to 1 upon s, means 1 upon -2, then that root also, means that pole will also lie in the left half plane. So either the value or its inverse, both will lie in the same plane. So we can analyze by putting s equals to 1 upon z in this equation and solving it in the same manner as we solve the basic Routh Hurwitz table. So there can be two methods to solve the characteristic equation or form the Routh Hurwitz table. When this happens, means this 0 comes in the first column of any row, then we can either put it by, means replace it by epsilon, a small positive value, and solve further. Otherwise we can, what we can do, we can replace s by 1 upon z and then form a new characteristic equation and solve that in a simple manner to analyze the final result. So this way we can apply the two methods. Let's check the previous year GATE problems that has been asked related to this concept. So this is the question that we have. Here what we have to find, we have to find the number of roots which lie in the right half of the S plane. So we have to form the entire Routh Hurwitz table, and then we have to analyze how many times the number of sign is changing, and then we will get the right half of S plane poles, and this is the characteristic equation. So let's check, let's solve it by the first method that we have studied just now. So here we have the solution using the first method, and we can see that this is the characteristic equation. We have formed the Routh Hurwitz table, and here we have got the result 0. So once we get the result 0, we will replace it by epsilon, that is epsilon is the small positive value, this is a small positive value, and now further we will complete the entire Routh table. After completing, what we will get, means we have to check how many times the number of sign is changing. So for the first, means s power 3 row, as epsilon is positive, so here positive, positive, and epsilon is also positive, so there will be no any sign change up to s power 3 row. Now come to the s square row, next row. Here we have to analyze it. So as we can see, epsilon is positive, this is positive, and when it is added with some positive value and divided by some positive value, so overall result will be again positive. So we have got the positive result again, so no sign change up to this s square row. Now we will analyze the next row, that is minus means s row. So here the result is minus 12 and the positive result of the previous element that we have just find that it was positive. So minus 12 into positive value minus 15 into positive value divided by some positive value, so overall the result will be negative. So this row comes to be negative, and the final row, final value will be of course 15, as we can see, because here is 0, here the element is 0, so we will get the final row as 15. So this way here also written the final element, final raw element will be 15. So from here, from the first element of the first column we have started positive, 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 and finally we have reached here to negative, and then finally again the positive value. So this way we have analyzed that there are 2 times sign change in the first column. So 2 times, if sign changes 2 times, it means 2 number of poles will be in right half plane and the remaining will be in the left half plane. So the result means the question was actually how many numbers of right half S planes. So it is the 2 number of right half S planes poles. Now see, solve the same question. We will solve the same question using the second method. As we have got 1 0 in a Routh Hurwitz table, so we can do it, means solve it by the second method. So suppose again we have this characteristic equation, so we will replace it by 1 upon z and form a new characteristic equation here. Now form the Routh Hurwitz table. We have formed the Routh Hurwitz table for this equation by putting the coefficients and all. Up to z power 4 row, means first two rows has been completed, and then finally the next row is going to be completed. And so we have found that this is minus 8, minus 4, half. Finally we have got this result. The entire Routh Hurwitz table has been completed, and there is no any such values has come, means in the first column there is no any 0 has come. So we can analyze that the situation that has come due to solving the s, means variable s characteristic equation, has not come if we have replaced s by 1 upon z. So this way we can very easily solve it and analyze the final result. Here we can see that positive, positive, no any sign change. Here we have got the negative result, again positive, positive, positive. So the sign change is what, where here from plus to minus and again finally plus. So only 2 times again the sign is changing. So the same result that we have got earlier, that there will be 2 number of right half S plane poles and remaining will be in left half plane poles, and that is 3. So this way we have solved the Routh Hurwitz special case using 2 methods. If there is only one element of the column will be 0, means in a row if the first element is 0, entire row is not 0, only the first element is 0, then we can solve it in the 2 methods, using the 2 methods that we have studied just now.